Let's try a similar problem to the last one, but now let's imagine that it's taking place on an incline. So we've got our mass sliding down an incline that is at an angle of 10 degrees to the horizontal. So we've got a 3 kilogram mass initially moving at 5 meters per second. Let's imagine that it slides for a distance of 4 meters. There is a coefficient of kinetic friction of 0.100, and the question is, what is the final velocity down here? Let me emphasize that this is the same kind of problem we've looked at before when we were using Newton's laws. But while we could use Newton's laws to solve this, let's use conservation, or let's use the work mechanical energy theorem. So we've got some work being done by a non-conservative force. Let's solve it that way. So what do we know? We know that the work done by the non-conservative force will equal the change in the mechanical energy. In other words, the final mechanical minus the initial, so K final plus U final minus K initial minus U initial. But now, because we're actually changing height, we do have to take into account the gravitational potential energy. Not spring potential energy, but at least gravitational potential energy. When we use a potential energy, we have to define our 0 point. So where do we want to define our 0 potential energy? Why don't we just define it at the lowest point in the problem? So we'll define 0 height at this height here. So here is our y equals 0 height, our origin for the y-axis. Well, our object is obviously starting out at some higher point, so we're going to have some initial potential energy. So what's the initial potential energy? Well, it's going to be mg y initial, so we need to know how far above our y equals 0 point is our object starting. Well, we know that it's sliding a distance of 4 meters. It's at an angle of 10 degrees, so what is this distance here? Well, that's just going to be 4 meters sine 10 degrees. So our initial height, y initial, will be 4 meters. I'm going to give myself a little more room. Y initial will be 4 meters sine 10 degrees, and that gives us an initial height of 0.695 meters. There we go. So we're starting at a little bit higher than where we're finishing, 0.695 meters. All right, good. What is the work done by the non-conservative force? Well, WNC is going to be F dot dr, our non-conservative force, dot, well, again, the force is constant, so we can just use F dot delta R. We don't have to worry about integrating this, although hopefully we would be able to if we needed to. What are we going to get? We're going to get the magnitude of the force, which is now kinetic friction, times delta R, or just delta x in one dimension, times the cosine of the angle between them. What's the cosine of the angle between them? Cosine theta. Well, let's be careful. What's the direction of the force? Well, the frictional force will be up the incline, trying to resist the motion as it slides down. What's the direction of the displacement? Down the incline. So what's the angle between them? It is, again, 180 degrees. We're going to have a cosine of 180. That's going to give us a negative again. Be careful. Just because you've got an angle in the problem, 10 degrees, and then we've got an equation, F delta R cosine theta, don't always think, oh, well, theta, it's 10 degrees. You've got to think about, what does theta mean? What does it mean in that particular equation? In the equation, work equals F delta R cos theta. What does theta mean? It's the angle between F and delta R. And in this problem, the angle between F and delta R is 180 degrees. So every time you've got to make sure that you think about, what do these values in this equation mean, and then you can figure out what values from your problem should they be. Okay, so here we go. We know that delta R is 4 meters. We need to figure out what the kinetic frictional force is. Remember that F kinetic is equal to mu k, the coefficient of kinetic friction, times the normal force, normal force, remember, not the net force in this case. What's the normal force for an object on an incline? Remember, we've seen this before, and hopefully you remember the normal force up this way, weight down this way. It turns out that the normal force is equal to the perpendicular component of the weight, perpendicular to the incline, and that turns out to be mg cos theta, where theta in this case is not 180 degrees, but it is the angle of the incline, 10 degrees. So the normal force here, F normal, will be mg cos theta, where theta in this case is the angle of the incline. So this is going to be 3 kilograms times 9.80 meters per second squared times cosine of 10 degrees. Hopefully that's squeezed in there so you can see it. 3 times 9.8 times cosine 10 degrees. Multiply that out, and we get a normal force of 29 newtons. And then Fk will be mu k, which is 0.100 times 29 newtons, 29 newtons, or 2.90 newtons. So there's the frictional force, 2.90 newtons. So what is the work done by the frictional force? We'll switch colors here. We're going to get a negative Fk, 2.90 newtons, times delta R. What's delta R? 4 meters. Multiply that out, and what do we get? We get the work done by the non-conservative force is negative 11.6 joules. Okay, there we go. Now, let's come back here to the work done by the non-conservative force. That is negative 11.6 joules equals, let's come back over here, K final. So that's what we're looking for. Let's stop for a second. Why? How do we know we're looking for that? We're looking for the final velocity. So let's find the final velocity. But how are we going to do that? Well, if we are using the work mechanical energy theorem, where does the final velocity come in there? It comes in as the final kinetic energy. So in order to find the final velocity, using the equation that we have, or that we're supposed to use, what do we have to find? To find this, we have to find the final kinetic energy. That's where the final velocity is. So the first thing we need to do, or I should say the next thing we need to do, is find the final kinetic energy, and once we found that, then we can find the final velocity. Sometimes someone solving a problem might go through these things kind of quickly, but without really explaining why we're doing something. But I want to make sure that you understand why, if this is what we want, the way to get that is to find the final kinetic energy. And so we've got to make that step in our minds. That's how we're going to end up finding it. Okay. Hopefully that makes sense. Plus the final potential. Well, what's the final potential? That will be the potential energy down here, but that's where we've set our zero height, so that is 0. So that's 0. Minus the initial kinetic energy. Now, the initial kinetic energy here is going to be exactly the same as the initial kinetic energy from the first problem. So just to remind us, Ke initial will be 1/2 mv initial squared, and those values are exactly the same from the first problem. So 1/2 times 3 kilograms times 5 meters per second squared. Multiply that out, and it's the same we had last time, 37.5 joules. Okay, so K final minus K initial minus 37.5 joules minus U initial. Now what is U initial? U initial is the potential energy initially. We found the initial height, so we need to find U initial. I'll do this over here. U initial will be mgy initial, which is 3 kilograms times 9.80 meters per second squared, times y initial, the initial height, which we calculated to be 0.695 meters. Sorry, it's getting crunched in there. Multiply that out, and what do we get? We get the initial potential energy is 20.4 joules. So then over here we've got minus UI minus 20.4 joules. There we go. So, what's the final kinetic energy? We'll take these over here. We've got minus 37.5, minus 20.4. That gives us a total of minus 57.9 joules. Bring it over here. We'll have K final equals 57.9 joules minus the work done by the non-conservative force, minus 11.6 joules, which leaves us with a final kinetic energy of 46.3 joules. And that must equal, the final kinetic is 1/2 times m times v final squared. So multiply by 2, divide by 3 kilograms, take the square root, and what do we find? We end up with v final equals 5.56 meters per second. There we go. Well, what do we notice? What is this mass doing? It started out at 5 meters per second, and now it's going at 5.56 meters per second. It's actually speeding up. It's not slowing down as it did in the first problem. It's speeding up. Well, does that make sense? Well, it is going downhill. So going downhill, we might think it should speed up, but there is friction. But notice the work done by friction, which is negative 11.6 meters, does not balance the energy gained, the mechanical, or I should say the kinetic energy gained from the loss of the potential energy. The potential energy is 20.4. So as the mass slides down, 20.4 joules of potential get converted to kinetic, which is going to tend to increase the kinetic energy, increase the velocity. Only 11.6 of those are lost to the non-conservative force. So we actually end up by increasing the kinetic energy, which we see here. We end up with a kinetic energy of 46.3 joules as opposed to 37.5 joules. So our kinetic energy actually increases because we're putting in more potential than we're taking out by the non-conservative work by the friction. Very, very good. Okay. Let's see if we can think about where is this energy going. Where is this energy going that's being used by the non-conservative force? Let's think about that just for one minute as we finish up. What we have found so far is that the work done by non-conservative forces on an object or maybe even a system of objects is equal to the change in the mechanical energy. So that if there is a negative amount of work done by the non-conservative forces, the mechanical energy will decrease. Where is this energy going? Is it just disappearing? Was it just going nowhere? Or what's really going on here? If we think about the forces, the non-conservative forces, in their very, very fundamental form, if you remember when we were talking about the 4 fundamental forces, there was gravity, the electromagnetic force, weak nuclear force, strong nuclear force. Frictional forces are essentially electromagnetic forces. So when you, and a very good example is, if you rub your hands together, there's friction between your hands. So is the energy due to the friction that's lost due to the frictional work, does that just disappear? Well, no. As you rub your hands together, the atoms and molecules on both sides of your, one side and the other side of your hands, they are rubbing against each other. And if you do it quickly, what do you feel? Your hands warm up. So what happens is the work that we think of as being lost to friction is going into energy that's kinetic energy of the atoms and molecules of your hand. But it's not kind of a coherent energy. It's like a random energy. It's what we think of as heat. So very often, especially with friction, energy that is lost to friction doesn't disappear. It goes into another form that we can't really use in general. Now, we certainly can use heat in some ways, but when we think of an object moving, if we think of an object flying through the air or something like that, and energy is lost, well, the object is not flying as quickly. It's moving more slowly, and that energy has gone into heat of the object and also heat in the air. But that energy does not disappear. It just goes into a different form, whether it's heat energy or energy in subatomic molecular forces, things like that. It doesn't disappear. So ultimately, and this is a very extremely important result, when we look at all of those energies, when different kinds of forces are used, but we look at where all of that energy goes, it turns out that altogether energy is conserved. The total amount of energy does not change. Sometimes it goes from more useful forms to less useful forms. That certainly happens, but the total amount of energy does not change. It is conserved. And this is an extremely fundamental, important law of physics. When experiments are being analyzed and it looks like energy is disappearing somewhere, physicists or chemists or whatever the scientist is that's looking at it just has to look more closely and try and figure out where is this energy going, because it's going somewhere. It is just not disappearing. It's not coming out of nowhere, and it's not disappearing to nowhere. So, energy is conserved. The conservation of energy. A very, very important result. And we'll be coming back to this in later lectures in all sorts of different ways. All right, very, very good. We've covered a lot of stuff here, and some of it was kind of complicated, but I hope it all makes sense. And I'll see you next time.